Hello viewers, thank you for visiting again. So we are going to continue with the course Designing and Implementing a Data Science Solution on Azure. So today's hands-on would be detect and mitigate unfairness within our trained model. I've opened this hands-on link here in a new tab. So what we are going to do as a part of this hands-on, machine learning models can often encapsulate unintentional bias that results in unfairness. For example, a machine learning model that predicts whether or not a patient should be tested for diabetes may predict more accurately for some age groups than others, with the result that a subsection of the patient population is either deprived of appropriate preventive health check or subjected to unnecessary clinical testing. Okay, so that unfairness could creep in our model because of uh, the data that we are quality of the data that we are using to predict the models. Okay, so how to detect and mitigate those unfairness. So for this hands-on, we have created Azure machine learning workspace and cloned the relevant notebooks required for this hands-on, and also created a compute resource which will be running our machine learning model. So I have covered this workspace creation including the notebook in my first video for this session and in this course. So you can visit that video using the icon I button. Click on the I button and you can go directly to that link and complete that prerequisite and then come back to this hands-on. So I've opened this Azure Machine Learning Studio and also started my compute resources here in this new tab. So my compute resources started and all the clone notebooks are here. So I'm picking this detect unfairness in our model. Okay, so I've opened this notebook here. Now, machine learning models can incorporate unintentional bias, which can lead to issues with fairness. For example, a model that predicts the likelihood of diabetes might work well for some age groups but not for others, subjecting a subset of patients to unnecessary tests or depriving them of tests that could confirm a diabetes diagnosis. Okay. So in this book, you will learn the FairLearn package to analyze a model and explore disparity in prediction performance for different subsets of patients based on each. So this FairLearn package will be used to explore disparity in prediction, okay, performance. And integration with the fairness package is in preview at this time. You may experience some unexpected errors. Okay, that's one warning given here. Important consideration for fairness. This notebook is designed as a practical set for fairness FairLearn package and its integration with Azure Machine Learning. However, there are a great number of considerations that an organization or data science team must discuss related to fairness before using this tool. Fairness is a complex socio-technical challenge that goes beyond simply running a tool to analyze models. Microsoft Research has co-developed a fairness checklist. Okay, let me open this for you. That provides a great starting point for the important discussions that need to take place before a single line of code is written. Okay, so you can download this checklist. Okay, there's a PDF link given here. I will also put the link for this in my video tutorial description section. You can go ahead and check that list. Okay, so we have to go through the checklist if we want more fairness to our model. Okay, install the required SDKs. So now we are going to install the required software development kits. To use the FairLearn package with Azure Machine Learning, you need the Azure Machine Learning and FairLearn Python packages. So run the following cell to verify Azure Machine Learning contribute fairness package installed or not. So let's run it. You'll also need the FairLearn package itself and the Ray widget package, which is used for FairLearn to visualize dashboard. So run the following cell to install them. So this is going to install the FairLearn package and Ray widget, which is a widget we can use to visualize the FairLearn or data or information within this Jupyter notebook itself. Okay, so the package is installed successfully. Next step is to train a model. So you will start by training a classification model to predict the likelihood of diabetes. In addition to splitting the data into training and test sets of features and labels, you'll extract sensitive features that are used to define subpopulation of the data for which you want to compare fairness. In this case, you'll use the age column to define two categories of patient, those over 50 years old and those 50 or younger. Okay. We are importing the relevant Python packages for test and training and test split for decision tree classifier algorithm from scikit-learn, NumPy and pandas libraries. Then we are importing the CSV file for diabetes patient, right, their data set. Then we are labeling the features and then we are marking which column we are going to predict. So diabetic column, right, which will be marked as diabetes or non-diabetic for each of the patient or each of the observations. Okay, get sensitive feature. So here we are marking age as the sensitive feature and then we are creating two age groups, right? Age group greater than 50. Okay, this is just slicing all the data into the age group where the age is greater than 50 years. Okay, so over 50 years and less than 50 years or younger, there will be two groups, okay, created. Next is data is split between training and test data set. Then creating a model using a decision tree classifier. Okay, so let's run this. This will create a model. So training model created, model trained. Now that you have trained a model, you can use the FairLearn package to compare its behavior for different sensitive features values. In this case, you will use the FairLearn section rate function to return the selection rate function to return the selection rate, that is percentage of positive predictions for the overall population. Okay, so that's what is called selection rate. The percentage of population prediction for overall population or the data set that we have. Use scikit-learn metric function to calculate overall accuracy, recall and precision matrices. Use a metric frame to calculate selection rate, accuracy, recall and precision for each age group in the age sensitive feature. We have two age groups, over 50 and less than or younger than 50 years, right? So two age groups. Note that a mix of FairLearn and scikit-learn metric functions are used to calculate the performance values. Okay, so we are using FairLearn matrices and scikit-learn matrix packages. We are importing selection rate and metric frame. We are importing from scikit-learn matrix accuracy score, recall score and precision score. Okay, So these performance values will be calculated. Get prediction for withheld test data. So whatever the test data now we have, we are going to pass it to our model for prediction, and then we'll be calculating the overall matrices, right? Then selection rate, then accuracy, recall, and precision. All these are being calculated. Okay. So overall selection rate is based on selection rate function. Okay. We get selection rate from the pair learn. Then we have overall accuracy, which is y test, y hyphen hat for accuracy score. Overall recall, so we are calling a recall function, recall score function. Then for precision score, we are calling precision score function. Okay. Get the matrices by sensitive group from fair learn. Okay. So from the sensitive groups, we are calculating matrices, and then we are calculating group matrices. So we will pass this matrix, right? And then we'll pass the sensitive feature group. Okay. So this is test group. So this will print the matrices for each group. Okay. So by group it is trying to print. Okay. And that group we created here. Okay. So let's run this as well. So here we see overall matrices. Selection rate, accuracy of our model is 89.7%. Recall score, precision score, right? Matrices by group. So we have two groups, younger groups, which is less than 50, and over the 50 groups, more than 50 years old groups. And for each of these groups, we are printing selection rate, accuracy, recall, and precision. Now from these matrices, we'll be able to discern that a large portion of older patients are predicted to be diabetic. You see here, this precision. Accuracy should be more or less equal for the two groups. This one, right? 88%, almost 18, 9 or 90%. But a closer inspection of precision and recall indicates some disparity. Here, these values are showing some disparity in how well the model predicts for each age group. Okay, so precision for age group more than 50 is lower, for less than 50 is lower, but for over 50 years old age group, we have higher precision, like prediction is more accurate. Okay. In this scenario, consider recall. These matrices indicate proportion of positive cases that were correctly identified by the model. In other words, of all the patients who are actually diabetic, how many did the model find? The model does a better job of this for patient in the older age group than for younger patient. Okay, so correctly able to identify whether patient is diabetic or non-diabetic for age group over 50. Okay, our model is performing better for this group. Okay. It is often easier to compare matrices visually. To do this, you will use the Fairness dashboard. Okay, and to run the cell below to generate a dashboard from the model you created previously. So we'll run this widget, RAI widget, which is from where we are importing Fairness dashboard, and this will provide a dashboard from the model that we created. When the widget is displayed, use the get started link to start configuring your visualization. So let's run this. Select the sensitive features you want to compare. In this case, there's only one, which is age. Okay, so select the model performance matrices you want to compare. In this case, it's binary classification model, so the options are accuracy, balanced accuracy, precision, and recall. We start with recall. Okay, so let's first get the dashboard, and then we are going to perform each of these actions one by one. Okay, so here we can see fairness is started. Let's open this. It is asking me to sign in. Okay, 1 minute. Welcome to the fairness dashboard. Okay, so dashboard is created and it has given me a link to get started. To set up the assessment, you need to specify a sensitive feature as performance metrics and a fairness metric. Sensitive features are used to split your data into groups. Fairness of your model across these groups is measured by fairness metrics. Fairness metrics quantify how much your model behavior varies across these groups. Performance metrics are used to evaluate the overall quality of your models as well as the quality of your model in each group. The difference between extreme values of the performance metric across the group is reported as the disparity in the performance. Then fairness metrics are used to evaluate the overall quality of your model as well as the quality of your model in each group. Fairness metrics represent the difference or the ratio between the extreme values of a performance metrics or simply the worst value of any group. So let's click on get started. So here we can see the age group. Click next and it asks me to first select the recall. So the fraction of data points classified correctly among those whose true label is 1. Alternative name is true positive. Rate sensitivity. Okay. So we have a something called confusion matrix. We'll have true positive, true negative, false positive, and false negative. So recall is just giving a true positive rate. Okay. Or sensitivity. So let's click next. Then it is select the type of fairness comparison you want to use. So we start with demographic parity difference. So we'll select demographic parity difference. Select next. So we selected sensitive feature as age and then performance metrics as a recall. Start with the recall and then fairness comparison I want is a demographic parity difference. I selected that one and it is calculating. So let's just wait. Once it is created, I'll show it to you. Okay, so I have opened the widget and we can see overall the recall, selection rate, demographic parity, false positive rate, false negative rate, all these things, right? You can see for over 50 years and under 50 years. Okay, so these two groups we can see, and here we can see selection rate, false positive and false negative rates. Okay, how to read this chart? The bar chart shows the selection rate in each group, meaning the fraction of points classified as 1. Okay, so for 50 or younger we have less selection rate, and for over 50 we have more selection rate. Okay, so I've opened this widget in the next tab, so it is running here in the next tab. Now the result shows a much higher selection rate for patient over 50, right? Here, and for younger patient than for younger patient. However, in reality, age is a genuine factor in diabetes, so you would expect more positive cases among older patients. If we base model performance on accuracy, in other words, the percentage of prediction the model gets right, then it seems to work more or less equally for both subpopulation. However, based on the precision recall metrics, the model tends to perform better for patient were over 50 years old. Okay, so let's see what happens if we exclude the age feature when training the model. So here we are removing that age feature, okay, from the feature lists that we had for the patient, right? And without age, then we are going to predict this diabetic column. So again, we are performing training and test data set split and training our model, and then checking fairness dashboard with sensitive features and the prediction of our model. Okay, we are passing all these values to fairness dashboard, and again it has created a new instance of fairness model. So let's open that new instance in a new widget. Okay, when you review explore the modeling dashboard, when you review recall, note that the disparity has reduced, but the overall recall has also reduced because the model now significantly under predicts positive cases for older patient, even though age was not a feature used in training the model. In training, the model still exhibits some disparity in how well it predicts for older and younger patient. Okay, recall disparity difference, demographic parity difference. Age is not part of the model, but based on the age we are checking the demographic parity, and we still see 30% and 59%. Okay, and still we see for over 50 years ages there is a high rate of uh, patient being the diabetic. Okay, so that's the selection rate. Here we had 69%, here we had 59%, right? And you see the selection rate is 69%, here 30%. It is changing, right? But selection rate is changing, but still we see the demographic parity difference, right? This underlines one the key difficulties in applying fairness to machine learning models. You must be clear about what fairness means in a particular context and optimize for that. Okay, so restart the model and upload the dashboard to your workspace. So you have trained the model and reviewed the dashboard locally in this notebook, but it might be useful to register the model in your machine learning workspace and create an experiment to record the dashboard data so you can track and share your fairness analysis. So we have to register our dashboard, fairness dashboard as well to workspace. Let's start by registering the original model which included age as feature. Now we are registering the model. Okay, so this is our workspace. Under workspace we are connecting to our workspace, then saving the trained model. Okay, then registering the model by naming it as a diabetes classifier. Okay, and then registered model.id, we are passing the id to that model for registering, and then we are printing whether model is registered or not. So here model is being registered, it's done. Okay, now you can use the fairlearn package to create binary classification group matrix set for one or more models and use an Azure machine learning experiment to upload the matrices. Okay, so fairness package will use to create binary classification group matrix set, okay, for more than one model, and then we will use Azure machine learning experiment to upload the matrix. So that's, we are automating it here. Create a dictionary of models you want to access for fairness. Okay, so this is for the age. Okay, and then we are creating a dictionary of models, model ID with diabetes model predict X, and then within that dictionary we are creating group matrices for different models for different group set. Okay, then we are naming the experiment as machine learning diabetes fairness. We are running the experiment and printing the run log. We are checking the dashboard, actually uploading the dashboard to machine learning with this name. That would be our dashboard name, Fairness Insight of Diabetes Classifier, and then uploading the dashboard dictionary. Basically here we are registering our dashboard within Azure Machine Learning Studio. Okay, and it's taking run configuration, our dashboard dictionary, which is group matrices dictionary, we are registering, right? Upload the matrices to Azure Machine Learning experiment. So that's what we are uploading here. Okay, this is our dashboard name, title, and then we are putting an upload ID to that. Okay, let's run this. To test the dashboard, you can download it. Okay, so this is what it is doing, and finally doing the complete run complete action, taking this experiment name and machine learning workspace. It is executing and registering the dashboard matrices within Azure Machine Learning Workspace. The preceding code downloaded the matrices generated in experiment just to confirm it's completed successfully. The real benefit of uploading the matrices to an experiment is that you can now view the FairLearn dashboard in Azure Machine Learning Studio. Okay. Run the cell below to see the experiment details and click the View Run Details link in the widget to see the run in the Azure Machine Learning Studio. So this is just to see the FairLearn dashboard and its details. Okay. Then view the Fairness tab of the experiment run to view the dashboard for the fairness ID assigned to the matrices you uploaded, which behaves the same way as the widget you viewed previously in the notebook. So these are the widgets that we saw, right? So if I run it, it is showing us this widget, right? Run is completed. Okay, and then if I click on view run details, it is going to take me to view run details, and then I'll go to Fairness tab, and here I can see the fairness dashboard. I can click on this fairness ID, and then I can see the widget here, performance matrix, fairness matrices. So I'll check the performance recall, and then next. For fairness matrices are demographic parity difference, and then click next, and I can see the same results here, selection rate, and then for false positive and negative rate here. I can check here. False negative rate predicted 0 while the true is 1, predicted 1 while the true is 0. So this widget is part of this fairness tab where you can see this widget directly. So that's it for checking the fairness widget. You can also find the fairness dashboard by selecting a model in the models page of the Machine Learning Studio and review its fairness tab. So I'll go to models, and then go to the fairness tab. This enables your organization to maintain a log of fairness analysis for the models you trained and registered. So this is our models. The last model that we created is this one. And if I go to Fairness tab, I can see the Fairness Insight for Diabetes Classifier. I can click here and check the fairness widget and do the same thing that we did earlier to see the demographic parity difference. So this is that, right? Then mitigate unfairness in the model. Now that you have analyzed the model for fairness, You can use any of the mitigation techniques supported by the Fair Learned package to find a model that balances predictive performance and fairness. In this exercise, you will use grid search feature, which trains multiple models in an attempt to minimize the disparity or the predictive performance for the sensitive features in the dataset. In this case, the age group. You'll optimize the models by applying the equalize odds parity constraint, which tries to ensure that models that exhibit similar true and false positive rate for each sensitive feature grouping. This may take some time to run, so maybe we'll pause the video for some time, but first let me run it. So this is importing grid search and equalize odds packages, right? Equalize odds packages for parity constraint, and grid search is to normalize the disparity, okay, of your data. Now finding mitigated models. So it's trying to find a model where unfairness is very less. Okay. So train multiple models. Training multiple models based on disciplinary classifier constraint, equalize odds, precise, fit. Just trying to fit the models. Save the models and get prediction from them, plus the original unmitigated one for comparison. So it is saving the original model with the unfairness, and then the models which has less unfairness or no unfairness. So it's comparing all those models, and then model name equal to diversity is unmitigated. So it's original model, and then mitigated model is the new model that we are creating with where the model is fair without any unfairness or bias. Okay, and then we can see these many iterations it has run. It is showing mitigated model 20 to 20 runs, right? So up to 20 models it has created. One is unmitigated and rest of the 20 models are mitigated models. Fine. Now you can use the FairLearn dashboard to compare the mitigated models. Run the following cell and then use the widget to visualize age by recall. So let's run this. And here we got a new widget URL. I can open it in the new tab. I'll do the same thing. Select the age group, select recall, and then select demographic parity difference. And we can see all the models, right? Mitigated and models, and all these mitigated models showing up here. Okay. So these are the key insight from the different mitigated models that we created and when we compared, right? So recall ranges from 17.5% to 85.1%. Demographic parity difference ranges from 5.92% to 70%. The model with the best performance achieves recall of 85.1% and demographic parity difference of 38.3%. The model with the best fairness metric value achieves a recall of 63.5% and demographic parity difference of 5.92%. You can download this plot as a PNG. Fine. So that's about comparing multiple mitigated models. Okay. So we are trying to mitigate and see the parity between each of these models. Okay. Disparity. The models are shown on a scatter plot. You can compare the models by measuring the disparity in prediction. In other words, the selection rate or the disparity in the selected performance matrix in this call recall. In this scenario, we expect disparity in selection rates because we know that age is a factor in diabetes, with more positive cases in the older age group. What we are interested in is the disparity in predictive performance. So select the option to measure disparity in recall. Okay. So we selected the recall for disparity. We already did recall and then demographic parity difference. Okay. The chart shows cluster of models with the overall recall matrix on x-axis and the disparity in recall on the y-axis. Therefore, the ideal model with the high recall and low disparity would be at the bottom right corner of the plot. At the bottom right corner, these two. You can choose the right balance of the predictive performance and fairness for your particular needs and select an appropriate model to see its details. An important point to reinforce is that applying fairness mitigation to a model is a trade-off between overall predictive performance and disparity across sensitive features groups. Generally, you must sacrifice some overall predictive performance to ensure that the model predicts fairly for all segments of the population. So upload the mitigation dashboard matrices to machine learning, Azure machine learning. Okay. So as before, you might want to keep track of your mitigation experimentation. To do this, you can register the models found by the grid search process, compute the performance and disparity matrix for the model, upload the matrices in an Azure machine learning experiment. So that's what we are going to do. Register the models. So all the models that we created as part of grid search, we are registering here within our workspace, passing model names and the model file. Okay. And prediction data. Create a group matrices set for binary classification based on the age feature for all the models. So group matrices we are creating, and then also those group matrices we are uploading within Azure machine learning. Okay. Experiment, and this experiment name is learn diabetes fairness. Okay. And then we will show the run details again. Also, we are trying to upload the dashboard to Azure machine learning. So this fairness dashboard we will be able to see for all the grid search based models that we are registering here. When the experiment has finished running, click the view details link in the widget to view the running Azure machine learning studio. You may need to scroll past the initial output to see the widget and view the Fairlearn dashboard in the Fairness tab. Okay, so first let's run it. Register the models, register the matrices, upload the matrices, upload the dashboard, and then we'll check the output. So each of these mitigated diabetes output up to 20 we saw, right, will be registered. 16, 17, 18, 19, 20. Okay, so it is showing as running and all the logs are being printed here. We see the view run details. Once this completes, then I'll click view run detail and I'll show you. So our script is completed, and then let's go to the view run details, upload it to edit this. So all these experiments, all these models for the experiment uploaded into our experiment section within Azure Machine Learning Studio. And here we can see fairness preview. Click here, performance matrix, recall, fairness matrix page, and then click next. And here we see all of these fairness dashboard, right? So we can see the widget now here from Fairness tab. Yeah, from here. So this is all about detecting and mitigating unfairness in our model. Please like and subscribe my videos. Thank you. Bye bye.